continuation of Stephen Hawking's scientific legacy. I met Hawking in '98 when I joined his research group in Cambridge, and somehow we found ourselves on the same scientific wavelength. What transpired was a wonderfully inspiring collaboration spanning 2 decades, a dozen publications, and in fact, our very last paper on the multiverse appeared just before his death on March 14. So people often ask me how it was like to work with Hawking. And especially for that, I brought a little video that shows the two of us at work. And it shows that it's in one way very normal. We calculate, we scribble, we talk, as theoretical physicists do all over the world. Of course, in a different way, it was also very, very special. Seriously entering into a conversation with Hawking required a huge effort. But it was like entering a different reality. His mind really roams the cosmos. But beyond his brilliance, what has struck me most through all these years is his passion. The man had an enormous passion for science, for physics, for understanding. In fact, a certain stubbornness in his search for truth. Hawking was one of these true seekers, as I view it. And so naturally our collaboration continued in the form of a kind of dialogue, I would say, spanning 2 decades. Gradually we grew closer because if you share the excitement of figuring out something about the Big Bang, yeah, that's exciting and it's a shared experience which is a lot of fun. We were often joined in our conversations and in our work by James Hartle, whose base camp is in Santa Barbara, California, who is here in the middle, and who is Stephen's compagnon de route from his early days, in fact. And of course, besides these conversations and getting together, there was the occasional email exchange. But I looked over my emails from Stephen after he passed away, and mostly these emails are about figuring out how we're going to get together next time and where we're going to get together. Stephen loved to get together. Here's one example, in fact, and in which we're making plans to go to Iran. We never made it to Iran, but he did make it to Brussels. Here's a picture on one of his visits to Brussels. Who knows where this is taken? It's a famous bar. Ah, yes, very good, yeah. So Stephen had an incredible joie de vivre. The whole thing evolved around physics, but physics went over into fun, and in fact, it was hard to see where one began and where the other ended. And it was just one great adventure. Now, many of you will know Hawking from his popular book, I imagine. As always with popular books, the actual content is in the subtitle, not in the title. In this case, from the Big Bang to black holes. So what I want to do today is to talk a little bit about black holes and about the Big Bang. The two are very closely connected, as you will see. So let's start with black holes before we deal with the whole universe. Black holes are black, right? But they are not just ordinary black objects. They're black in a much more profound way. That is because black holes exist in Einstein's theory of relativity. And Einstein's theory describes gravity in terms of the warping and bending of the fabric of space. Here, for instance, the mass of the Earth is creating a valley in the fabric of space, and the moon, as if automatically, circles the Earth. Similarly, the sun is creating a deeper valley which keeps the Earth into orbit around the sun. That's Einstein's worldview, that's Einstein's theory of relativity. We're talking 1915. It's the foundation for all of Hawking's work. Einstein's theory was tested very quickly in 1919, because if the sun is going to create some sort of a valley in the fabric of space, if you send a light ray around the sun, skirting the surface of the sun, that light ray will also move through that valley and gets a little bended. That bending was observed in 1919 during a solar eclipse in an expedition launched by Eddington to West Africa, where the solar eclipse was taking place. Now imagine, at the end of the life of a star, stars implode, heavy stars implode. But when stars implode, in Einstein's theory, that valley in the fabric of space around it is going to get deeper, a lot deeper. It's going to get so deep that light rays coming too close are going to be trapped. Then you have a black hole. And black holes in Einstein's theory were found very quickly after he formulated it by Karl Schwarzschild, who was working on the Russian front during World War I, and who sent the black hole solution of Einstein's theory on a postcard to Einstein back in Berlin. And he wrote at the end, I think, something like, well, thanks for your theory. It gives me the opportunity to get away from the whole thing here. Now, Einstein, incidentally, didn't like it. He didn't like it at all. He wrote back to Schwarzschild, said, if that's true, that's a disaster. And in a way, he was right, as you will see in a minute. But now we do know that black holes exist. We know this because just a couple of years ago, the LIGO experiment in the United States, with that L shape here, has measured the gravitational waves which are being emitted when two black holes meet and collide. Those gravitational waves tell us that story of that collision in great detail, and have shown us that black holes, billions and billions of black holes, do exist in our Milky Way, in our universe as a whole. But other than gravitational waves, when they meet each other, black holes are black. Or are they? Here we come to Hawking's first major work. He decided in 1974 to put that idea to the test. And he said, look, let's think about empty space. But let's think seriously about empty space. At a microscopic level, our world is governed by quantum theory. And empty space is in fact a very lively thing. Constantly, particles are being created and annihilated in empty space at a microscopic level. Quantum theory, the vacuum in quantum theory, is in fact a rather turbulent thing. But we don't see this because the particles exist for a fraction of a second and then they disappear again. So here we have it, so that's what I'm indicating there. Now, Hawking said, let's put a black hole in this empty space. What happens? He found, to his annoyance and surprise, was that the black hole makes some of these virtual particles become real. Particles which are being created near the surface of a black hole can become real particles, because one of the two can enter the black hole, making it possible for the other one to convert itself into a real particle and go away. So to Hawking's surprise, near the surface of black holes, that quantum process of vertical particle creation is a real thing. And so he found that black holes, in fact, are not so black as everyone thought. Black holes radiate, which became known as Hawking radiation. Black holes have a temperature. It's a very, very small temperature. It's an exceedingly small temperature. In fact, it's colder than the temperature of the universe as a whole. Nevertheless, the effect exists, and it means that if you wait a long time, eventually black holes will shrink and evaporate. In fact, that itself led to quite a few puzzles, because if a black hole evaporates, you no longer know what made it up in the first place. And so in his typical, somewhat provocative style, Hawking said, well, Einstein, God not only plays dice, he also sometimes throws the dice where they cannot be seen. And this question, whether black holes ultimately destroy information, or whether they store information in some ingenious way we haven't figured out, is in fact one of the central questions in theoretical physics today. Now, to give you some context, we're talking about 1974, and these became one of the most famous papers in physics of the 20th century. Now, I asked Hawking how his work was received back then, in 74. And he replied, only 8 people showed up for my seminar. So when he presented his work, no one was interested. No one thought of it as being important, and this shows, in fact, how far ahead he was of the pack, so to speak. Eh? Now, any object which has a temperature will also have an entropy. And that rolled out of the same calculations. And this is the only formula I'm going to show you today. So enjoy it. And that's the formula for the entropy of a black hole. The entropy is on the left. Yes, on the left, right? And so it's given by a product of 2 ratios. Forget about the first ratio for now. We'll deal with that later. Focus on the second one, A over 4. A stands for the surface area of a black hole. Now, all engineers among you should say, whoa, wait a minute. The entropy of an object is proportional to the volume of the object. It's not proportional to the area, the surface of an object. And you're absolutely right, except for black holes. There's something very special about black holes. Why is the entropy proportional to the volume? Because you can do a lot. Entropy is connected to information, and you can change configurations in the volume of an object, and therefore account for the microstates making up the entropy. Not so for black holes, it seems. The black hole entropy is proportional to the surface area of the black hole, which suggests, but it's not proven yet, but it strongly suggests that in fact we better think about black holes purely in terms of their surface, the surface of the region of collapsed stars, which can no longer communicate with the outside universe, and that we forget about the inside of black holes. In fact, maybe there is no inside of black holes, and that is the current line of thinking in the field. Hawking's calculations have given rise to explorations of black holes in what we call holographic terms, in which we project the black hole onto a surface, and we deal with the surface only, and we capture all information, because the entropy is proportional to the area of the surface. But we're not done yet with this one formula that I'm showing you, right? We have all these other letters to deal with. So there's a second point about this formula, which is rather exciting, which is it's the only formula in the whole of physics in which all these letters appear. Now, that may not tell you very much, but I'm now going to tell you what these letters are. This is the explanation of these different letters. K stands for the Boltzmann Constant, so it's a number which makes us think of thermodynamics. C is the speed of light, which makes us think of Einstein's relativity. H bar is Max Planck's quantum constant. It's quantum theory. And G, as you know from your high school years, is Newton's constant of gravity. There is no other formula in physics where gravity, quantum theory, relativity, and thermodynamics appear in one single equation. That is the true depth of Hawking's result about Hawking's work on black holes. And in fact, it still sort of feels new to us. We still don't quite understand what it means. Where is the information? Where are the quantum bits of information that make up a black hole entropy? It's still very much an active area of research, and in fact, getting a better understanding of this formula, of those quantum bits and where they are stored on the surface or inside or whatever, is pretty much the holy grail of theoretical physics these days. So, in a sense, what this formula is telling us, it's the very first glimpse it is giving us of a unification, of Einstein's dream of a unified theory, of the microscopic world, quantum theory, and the macroscopic world, gravity, space-time, and so forth. And it's black holes, and the study of black holes, which is going to further elucidate how that union works. Black holes are very much the atoms, so to speak, of the 21st century. The study of the atoms in the early 20th century, it gave us quantum theory. The study of black holes may guide us towards a theory combining quantum theory with gravity. Finally, there's a sociological reason why I gave you that formula. Next time when you go to London, swing by Westminster Abbey, and you'll find it there, engraved on Stephen's tombstone. In 2 weeks, the Dean of Westminster Abbey is offering a Thanksgiving service for Hawking, and he has agreed to have that formula engraved on Hawking's tombstone. In fact, he had it wrong the first time. We had to correct him just 2 weeks ago, but I think it's all set now, and I think we're good. By the way, it is not the first formula in Westminster Abbey, I found out, so the Abbey does formula. Okay, so let us now move to the Big Bang. Hawking's interest in the Big Bang came when he moved from Oxford to Cambridge. So he was a student in Oxford. He didn't do anything, and Oxford took the exceptional procedure of offering him an oral exam to decide whether to let him have a first degree, in which case he would go to Cambridge, he would be admitted to Cambridge, or a second degree, in which case he would stay in Oxford for his doctorate. He got a first, and so he went to Cambridge, which must be, frankly, one of the worst decisions Oxford ever made. But there he goes. So this is Stephen's life in Oxford. But then in Cambridge, he gets assigned to Dennis Sciama. Dennis Sciama is one of the pioneers of modern cosmology and a kind of fundamental thinker. And he assigned Stephen to think about time, what it means fundamentally, our notion of time. So Hawking wrote a PhD thesis, as everyone's supposed to do, in Cambridge. The title is Properties of Expanding Universes. But what's especially important here is the date. We're talking 1966. Now, as you all know, 1966 is a key year in modern cosmology, right? For two reasons. Of course, expanding universes were known. I mean, expanding universes are a Belgian invention, as you know, right? So George Lemaitre came up with the idea of an expanding universe. Here is George Lemaitre. You might have thought Einstein came up with it. I mean, he could have come up with it. After all, he had a theory. But as you can see on the picture, he didn't really like it. Right? This is a sketch by Lemaitre of one of the first sketch ever made of expanding universes. This is time, and here is the size. What does it mean in practice, an expanding universe? It means that the distance between galaxies increases as time goes on. But of course, that also means that if we reverse time, go backwards in time, that galaxies get closer and closer to each other, and in the end, they're all on top of it. And that was the problem. If this business about expanding universes was right, then surely the universe must have been very hot in the past. Where is all that heat? That was the reason why people were reluctant to really embrace the notion of an expanding universe. The heat can't just go, right? Because the universe is all there is. So it can't go anywhere. The entire universe was like a hot fireball. So where is that heat? That was the question. And that's why 1966 is such an important year. Because in 1966, these two gentlemen, Penzias and Wilson, two engineers working at Bell Labs, discovered and working on intercontinental communication, radio communication, discovered noise in their giant antennas. And the noise was everywhere. They tried to avoid it by turning their antennas, and they couldn't get rid of it. And it really frustrated them, to the extent they went to their physics colleagues in Princeton asking, can't you guys do anything about this noise? And in Princeton they said, well, listen, wait a minute. No, we can't do anything about it. This is the noise from the Big Bang. And this is how it looks like. This is a projection onto a plane of the sky, in which I'm not showing you the planets or the stars or even the galaxies. I'm only showing you the heat that we receive from different directions on the sky, which comes, in a sense, from behind the furthest galaxies, behind the furthest stars. And as you can see, this is probably the most boring, important picture in the world. The heat is the same from different directions. That is because the Big Bang was just some homogeneous hot fireball which then cooled down. Now it's very cold. 2.7 Kelvin, and a Kelvin is minus 273 degrees, so it's cold. Incidentally, it's hotter than these black holes, which I was talking about. The black holes have an even lower temperature. So that's the first discovery. During Hawking's PhD thesis, the heat of the Big Bang was discovered. So he switched subject. You can see this in his thesis. During the last year, first he was talking about all sorts of things. The last year he said, wait a minute, is this business about expanding universes is true? If it's true all the way back to when the universe was really hot, so we have this radiation, probably it's going to be true all the way back. So he got to work with Einstein's theory of relativity and traced the evolution of our universe backwards to see what happened. And what happened is the main result, so that's the second reason why 66 is important, it's the main result of Hawking's thesis, in which he showed that if you trace the evolution of an expanding universe backwards, you end up with a genuine beginning. And by a beginning, I mean a beginning in the most profound way you can imagine, and then even a little more profound. Okay? I mean an origin of time. Hawking showed that, according to Einstein's theory, an expanding universe must have a beginning in which time basically falls apart in what he calls a singularity. A singularity is basically saying, okay, we don't know what happens. But I'm putting an emphasis on this because this result, in my interpretation, touches on the core of Hawking's thinking. Because if we go backwards and Einstein's theory falls apart, then it's quite clear that cosmology as a science has a major issue. It has a major issue because you can't get going in a controlled manner. You sort of have to have a leap of faith to get the universe going, and from then onwards, everything is fine. And so Hawking became obsessed with these questions about the Big Bang. Questions like why our universe is the way it is, why it exists at all, whether it's unique, all these kind of questions he realized at the end of his doctorate lie squarely beyond Einstein's theory. So in a way, also in cosmology, to get to a truly predictive framework, scientific framework, in which you could sort of complete cosmology, you have to go beyond Einstein's theory of gravity and space-time and merge it with quantum theory. Now you might say, well, is this really important? It's a long time ago, and so forth. And in the case of black holes, you have a point. Because all that I did with this quantum theory and that vacuum and blah, 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 in the end I told you, okay, black holes radiate, the temperature is so small that you're never going to see a black hole explode. You're never going to do an observation to test this. Yet, the formula of Hawking is probably right, so it's good to have it on its tombstone. But here, you're not going to escape so easily. Because in cosmology, when it comes to the Big Bang is in our past. We are, so to speak, inside the black hole here. We are a consequence of what happened at the Big Bang. And to make matters a little worse, it turns out that you got the universe going in a very, very special way in order for the rest to work. In order for billions of years later, for there to be structures and galaxies and planets and Brussels and all sorts of things, okay? You have to get it right at the Big Bang, otherwise it just doesn't work. So there's a major issue in cosmology, and that is the reason why Hawking was so much focused on the Big Bang. Black holes were a playground for him. The real game was the Big Bang. And the questions that he asked at the end of his doctoral thesis are there for 50 years behind all of his work. He was very, very focused because he realized that those questions were a gateway to get a deeper layer of understanding. A kind of understanding, not like just how our universe gets on, but why it is the way it is, how it fits so nicely together. It turns out that our universe seems somehow delicately fine-tuned. It all hangs together beautifully in order for structures to emerge. Now, there was some guidance on this from these observations. You remember that picture which I showed you, taken by the engineers from Bell Labs. Now, once that picture was taken, physicists geared up and developed satellites specifically designed to measure the afterglow from the Big Bang. You could think of this as a picture of our universe that shows how it was a couple of 100,000 years after the Big Bang, when it became transparent for radiation. And when those satellites were launched, a major moment, so you measure the temperature more and more precisely with every satellite you build, basically, yeah? And at some point in '92, all of a sudden, it was revealed that the temperature was not exactly 2.7 Kelvin, but that there were small variations. The Big Bang was flickering. And some regions on the sky were a little warmer than others. The difference is very, very small, 10 to the minus 5. And then more satellites were built to measure it even better, and look, a whole pattern was revealed. Now you can say, well, this looks random. Indeed, it looks random to the naked eye, but in fact, there are all sorts of correlations between the temperature in different directions on the sky. And there's a whole story behind this picture, and that story is the story of the Big Bang. Because that is a snapshot of the universe as it was 300,000 years after the Big Bang. What created that pattern? Well, that's the physics of the Big Bang. So this is the main observational guidance we have. It's a kind of Rosetta Stone in cosmology, which we have in order to interpret or match our theories or models of the Big Bang. One important avenue was also invented here in Belgium by François Englert in the late 70s, who toyed with the idea, which later became known as inflation, cosmic inflation, that maybe the universe in the first fraction of its life underwent a very rapid phase of expansion, much more rapid than it does now, in which it expanded basically from the size of an atom to, say, an apple. What became clear a couple of years later is truly remarkable. What became clear was that such a rapid phase of expansion has a similar effect on these virtual particles in the quantum vacuum, which we talked about earlier, than the horizon, than the surface of a black hole. If the universe expands really rapid, then the expansion of the universe stretches these particles from apart and also converts these virtual particles, which would under normal circumstances disappear immediately, converts them into real particles. And these real particles show up hundreds of thousands of years later as those patterns of temperature fluctuations in our Big Bang afterglow. So there's a beautiful story here, which connects at the very beginning, the earliest phase of our universe, to our Rosetta Stone. And those fluctuations, those temperature variations, are crucial. They're absolutely crucial. Because if you fast forward the evolution of the universe, the blue regions of the Big Bang afterglow will condense and will turn into gas clouds, where eventually you will have the first stars and the first galaxies that appear. And the universe becomes more and more clumpy and develops larger and larger structures, galaxies, and ultimately the planets and life at least on planet Earth, and the satellite with which we look at that. That's the evolution of 13 billion years in 1 minute. But it wouldn't have happened if it weren't for that initial pattern of fluctuations, those initial flickers in the Big Bang afterglow. And those flickers wouldn't have been there if the universe hadn't come into existence with a brief burst of very rapid expansion, which stretches these vertical particles into real ones. So we have a sort of unity. Modern cosmology gives us an amazing unity of 13 billion years of evolution, tied all together. Except for this one question. What started inflation then? How did that go? And indeed, you can always go backwards. And that's the question which remained. And in what Hawking regarded as what he regarded himself as his most important contribution to science, in 1983, he comes up with a suggestion for replacing that question mark by something else, by a mathematical model. Roughly speaking, he said, wait a minute, if that rapid expansion can transform vertical particles into real particles, maybe a similar process all the way at the beginning can create a pair of universes. And that became known as Hawking and Hartle's no boundary model, which is basically a mathematical model, quantum model, through which you can understand how our usual notions of space and time can arise. And you see that at the moment of creation, what is basically happening is that our normal flow of time, which I told you stops at some point, according to Einstein's theory, the time dimension basically merges with these space dimensions and sort of naturally closes off the universe, as if the Big Bang were, the ultimate horizon, so to speak. And then you have that second universe going that way, but don't worry about that. That's pretty much disconnected. Now, amusingly, or maybe coincidentally, I don't know, Hawking went to the Vatican before he did this work. There was a conference on astrophysical cosmology organized by the Pontifical Academy of Sciences, and as if he wanted to get some approval, he mentions for the first time this model, not in detail, but just vaguely in words, at that conference in the Vatican. So he writes there ought to be something very special about the boundary conditions in the past of the universe, about the Big Bang. And what could be more special than that it has no boundary? Again, this is the same kind of question which I explained comes up after his doctoral thesis. It's really the question, can we use science to get a handle on the origin itself of the universe, or are we somehow limited in a profound way when it comes to the actual emergence of space and time? So the obvious question you're now going to ask, well, what is there before the Big Bang then? The answer in Hartle and Hawking's model is, well, your question does not make much sense, because try to get before the Big Bang. First you run backwards in real time, but then you're forced into a kind of closure of the universe, just like the Earth closes everywhere, right? What's north of the North Pole? What's south of the South Pole? The question doesn't really make sense. Okay, but so far it seems all good. In the late 90s, we figured out that in fact, that kind of model of the Big Bang predicts that our universe does come into existence with a rapid burst of expansion. So the model goes nicely together with the idea of inflation and the flickering pattern we talked about. But gradually, when we looked more into the implications of Hawking's model of the Big Bang, it dawned upon us that in fact there were all sorts of ways of creating universes. And so it became sort of a game to create all sorts of universes. That was fun for a while, but at the end of the day, we were stuck with a gigantic multiverse. So the quantum creation mechanism, which he had set up in the 80s, worked a little too well. And undermined, in a way, its own success. Because now we had all sorts of universes, be it parallel or in some gigantic space, I don't really care all that much. The point is that the uniqueness which Hawking sought when it comes to cosmology and a theory of the Big Bang was lost again. We could create different universes. Some were habitable, others were not. Some were going on for billions and billions of years, others were short-lived, and so forth. It was very difficult, it became very difficult to get a handle on that multiverse, and that's what ultimately led to our final range of papers, in which we went back to the roots of his original model of the 80s and looked at it again in light of new developments, in particular the notion of holography, which I talked about earlier. So I mentioned that it might be better or more fundamental or more precise to think about black holes in terms of physical theories defined on their surface. Once you have a physical theory defined on the surface of a black hole, you never need to talk about the inside. In fact, we realized that similarly, here in this quantum creation process, we could reformulate his original theory in what we call holographic terms. In fact, we could get rid of that closure, that sort of imaginary time dimension there, and project it out onto what became an initial surface, a holographic surface, which basically captures all you need to know about whatever came before the Big Bang. It really describes a timeless, primeval quantum state, very much incidentally how George Lemaitre originally envisioned the origin, from which gradually our normal time dimension emerges. Again, to our surprise, so we had a new formulation of his old theory. So the first thing we did, of course, was to look again, well, where's the multiverse? So we looked at what kind of universes could emerge from that new theory of the Big Bang. And we find that in fact, the multiverse was basically gone. The universe which comes along is very much uniform like what we observe, and it appears also to be finite. And all the way at the end, when we were completing this last paper, yet again, I was very much impressed by Hawking. Because evidently towards the end I was driving our work, and he was very well realizing that this was going to end up against his original theory of the 80s, with a central piece of which was that closing region, the fact that there was no boundary. But Hawking realized all through his career, he was never too shy to give up his old ideas or to change his mind or to try new alleys. And throughout his last collaboration, from one day to another, yet again, he completely changed his mind and said, like, listen, maybe there is an initial boundary, that's the way to go, go holographic, so to speak. And so we completed this just before his death. Yeah, the paper appeared in the end, just after he passed away. So that's the story of my collaboration with Hawking and his broader scientific legacy. Thank you.